as has been mentioned, I'm going to tell you a little bit more about radiation in a talk which is subtitled Cosmic Rays Bite the Dust. So hopefully you'll see why in a bit. All right, if I can advance the slide. All right, so in order to talk about radiation chemistry and radiation chemical processes, we have to talk about stopping theory. So what do we mean by stopping theory? Well, I'll get around to it, but I'll kind of do a circuitous route. First, we'll start with a historical overview. In 1896, Henri Becquerel discovered radioactivity, except A, they didn't know that it was radioactivity, and it wasn't called radioactivity. What Becquerel found was that uranium salts were messing up his photographic plates. Well, he was doing experiments, and he thought they were making X-rays. Turns out they're making something which were called immediately afterwards Becquerel rays, and later, in 1898, Marie Curie and Pierre Curie started working on this. They called it radioactivity. And Marie Curie made the very astute observation that the alpha rays that she was seeing were losing velocity as they traveled through matter. One of the remarkable things about this observation is that she made it before we had the modern model of atomic structure. So they had no idea what alpha rays were or how they could be losing matter. They just knew that from experiments, that's what they were doing. All right. Moving a little bit forward in time to 1912, J.J. Thomson discovers the electron, or he discovered the electron previously, and then in that year he wrote the first theoretical paper on how charged particles lose energy. Now the field has evolved a bit, but we still use a lot of the notation from this early theoretical paper. Then in 1913, Niels Bohr wrote a paper with the very short title, On the Decrease of Velocity of Moving Electrified Particles on Passing Through Matter, and he swiftly followed it up with a paper with the radically different title, On the Decrease of Velocity of Swiftly Moving Electrified Particles in Passing Through Matter. Now these were landmark papers. They sort of helped make his career, and we still use a lot of the theory that he developed in talking about how charged particles lose energy. Here's one of the things which we still use a lot, and it's to divide the types of collisions which a charged particle encounters on moving through matter into two main categories. One of them, let's see which one is the laser. There's laser, conveniently colored. We call nuclear or elastic collisions. And this is when the charged particle is losing energy to the nuclei in what we call the target. The other is called electronic or inelastic collisions, and this is when the charged particle is losing energy to the electrons. So this comes from Bohr, and we still use it. So finally, in our historical overview, in 1932, Hans Bethe applied the very latest in quantum mechanics and relativity to stopping theory. And the Bethe formula for stopping power is still widely used. Oh, okay, now that works. Right, so now that I've told you about how the theory of stopping power has developed, I'm going to tell you what it looks like when you put all the physical processes together. And so you can divide the timeline of what happens when a particle is moving through some matter into three main stages. So in this first stage, the physical stage, molecules are ionized and excited. This is very fast. And so what happens is you produce a lot of charged species and species in electronically excited states, which go on in the physiochemical stage to recombine electronically, so charges are neutralized. And this results in dissociations. And then some of the excited species can also dissociate. When you're talking about irradiation in solids, species on or near the surface can also get kicked off in a process called sputtering, which is very complicated. So in the physiochemical stage, what you're left with are a bunch of really reactive fragments and radicals, and they can do chemistry in the chemical stage. So you'll notice this is the longest. It's also been the hardest to simulate. But in this case, what happens is, at least in solids, the species that you've made can sort of move around, as you saw in Brandon's talk, and if they encounter one another and can react, they can do so and form strange new molecules. All right, so here's what it looks like all together. Now, for reasons which will become hopefully obvious later on, imagine that this blue block is an O2 ice. And you've got a proton coming in, and what happens? Well, as I mentioned, during the physical stage, it can ionize species or excite them. And these electrons produced in the ionizations are referred to as secondary electrons. Confusingly, here electron A is called a first-generation secondary electron. And if it has enough energy, it can go on and further ionize species, creating, also confusingly, what's known as a second-generation secondary electron. And these can excite species as well. Now, when they lose enough energy through collisions, these secondary electrons enter what's called the sub-excitation regime and can do strange and bizarre things, like where you can have a 4 eV electron breaking a 5 eV bond, thanks to the magic of potential surfaces. All right, so that's track structure. Now I'm going to tell you a little bit about a new model I wrote, which can do the physical, the physiochemical, and the chemical stages of irradiation. It's called Serous. Serous, it's not Chris, that would be a little bit too vain. It stands for the chemistry of ionizing radiation in solids. As you can see, I could have called it Chris, but that would have been a little bit too rich. So it's a microscopic Monte Carlo model, which, as far as I know, is the first one which is able to combine the atomic physics calculations again and the chemistry. So you're able to do that long chemical phase as well, where you have things moving around. And so again, we use the kinetic Monte Carlo method for that. Here's the paper recently came out where I described it. And just as a quick side note, the model was written in Fortran. It's a matter of local pride that I have to mention that in 1956, the Fortran project at IBM was headed by this fellow, John Backus, who was a UVA chemistry undergrad. Just a little bit of Fortran trivia. All right, back to the science. So in trying to simulate tracks, my initial attempts were not very impressive. So what do we have here? Well, imagine you have an O2 ice and you have a proton entering right here. It's moving through, and randomly, since this is a Monte Carlo model, it's having collisions. And so these points represent either elastic collisions or inelastic collisions, or which can be ionizations or excitations. So that's nice, and I was certainly very happy when my model started to do something I wanted it to do, but it's not very impressive. So you may be slightly more impressed with what we can do currently, if I can get the video to play. Wrong side. All right.
Hit escape while you're in the PDF.
Uh-huh. Okay. There you go. All right. So here's what we have now. Circa 2017, what we have is similar to the first plot I showed you. I'll replay that. You have a particle coming in here, a proton, moving through your O2 ice, except now you can see all of the secondary electron tracks. So these meander around randomly and do those excitations and ionizations and then those funny things they do when they lose enough energy. So we can do a little bit better today. All right, back to full screen. Yeah. Theorists are the worst at using technology sometimes. All right, so yes, so there it is. So now I'll finally tell you why I've been talking about O2 ice, and that's because chemically, for an irradiated system, it's about as simple as you can get. So we found this experiment. We wanted to simulate a well-constrained experiment rather than the fairly well unconstrained interstellar medium. And so we found this one, which was done here at UVA. That wasn't a requirement, but it was certainly a perk, where oxygen ice was irradiated with 100 keV protons, and ozone was synthesized. And the ice was kept at 5 Kelvin under ultra-high vacuum and was about 10 microns thick. Keep this number in the back of your mind. All right, so here's our $64,000 question. Once we had the tracks, could we combine it with the chemical model and actually do chemistry? This was the part which had never been done before. So let's talk about our chemical model. A Monte Carlo model is a little bit like waiting in line to board a plane. It's like this now, right? And a game of three-dimensional chess. All right, so how is it like a game of three-dimensional chess? Well, this is just a more detailed version of what you saw earlier in Brandon's talk. You can imagine this is looking down from an alien's eye view on the surface of an ice. You can have things coming in from the gas phase onto the grain, desorbing or hopping around. And again, if they encounter a co-reactant, they can react. And then imagine this being sort of a dollhouse top to bottom slice. And the blue squares represent lattice sites. We call them normal sites. And the yellow squares are interstitial sites. And these enable diffusion throughout the solid. So as you see here, things can move around and react when they encounter a co-reactant. That's just a simple picture of how it's like a three-dimensional chess game. So putting it all together, here's the basic algorithm of the Serous model. So when you start your program, the first thing which happens is it gets smacked with a proton. And so you calculate the track. Then you evaluate your ending condition. And if the model isn't over yet, you go back and figure out what the next thing is. Since it's a Monte Carlo model, everything has to wait for everything else. Only one thing can happen at a time. And you just keep going through this loop until you reach your exit condition. But now, when a neutral species hops, this is where the chemistry happens. Because, as I mentioned, if it encounters something it can react with, you form a new product. So we have the chemistry over here. We have the track calculations over here. It combines all together into a model which can do some cool stuff. All right, so chemistry. As I mentioned, the O2 system, you can think of it as having a fairly simple chemistry. You have your O2 getting broken apart by X here, meaning radiation, into two oxygen atoms. Those oxygen atoms can combine with molecular oxygen to form ozone, stabilized by a third body. The ozone can get broken apart and can also react with oxygen. So it looks like a fairly simple system. But now this is from the point of view of a typical rate equations type chemical model. What does it look like from the point of view of a detailed Monte Carlo-based model where you're dealing with excited species and ionized species? So here is the reactions table from our paper. We have more than an order of magnitude more reactions than that simple system that I showed you before. We have, as I mentioned, we have ions, we have excited species, and these become very useful in actually doing the chemistry because you have to make a lot of approximations in this sort of regime. So I've beaten around the bush, but here are our final results. Here is ozone concentration. Here's fluence. Fluence just means how many particles you've smacked into your solid. And you can see in our, the blue are the experimental data. In yellow, we have our standard model results. And you can see we get the steady state abundances of ozone fairly well. So we were happy about this, but we noticed we were at higher fluences than the experiment. So we thought about it a little bit and realized, oh, it's probably because what we're doing, this is a thinner ice than the experiment actually used. So you're depositing less energy per particle into it and making less ozone per particle. So this was a 0.1 micron ice. We simulated the effects of having a 1 and 10 micron ice. And the 10 micron ice reproduced the experimental data very nicely. And as you remember from the earlier slide, the experimental ice was about 10 microns. So not only do we predict the steady state abundance, but we also are able to roughly predict the thickness of the ice. So we were very happy about that. All right. So with that, I'd like to thank my advisor, former fellow group members, collaborators, and I'll leave you with this last slide from the pre-Fantastic Four.
Questions?
This might be a very naive question, but so in your, when you had your proton that hits your ice, you have all these tracks, they seem to have the same width. And I was wondering if you have more energy when you come in, that you have more secondary electrons, and the width will be larger at the beginning, and
yeah.
like something
Yeah.
like that.
That's a good question. So the, I'll go back. So there's a funny relationship where the higher the energy of the primary particle coming in, the smaller the cross-section, so the fewer secondary electrons they're going to make. Now, the sort of width of this is actually determined by the average secondary electron energy. Now, you can get very energetic electrons coming off this as well. Those are called delta rays. And so since this is random, you see some of them don't go very far, some of them have more energy. So since this is a stochastic model, you get the luck of the draw, but this is as it is in nature as well. It's based on the average electron energy, which is sort of a skewed Gaussian type distribution.
All right, Chris, I got a question for you.
Cool.
So can you do this with a water ice?
Yes, there's, so we just, that's one of the next things that we're looking to do is water ice, because clearly water ice is the most astrophysically relevant ice. And so the reason why we didn't want to do this water ice first is because hydrogens make everything complicated, and O2 is relatively simple, as you saw at least in the rate equations type approach. So that's the next step.
Yeah. My follow-up is what happens when you add dust too?
When you add dust too, so you mean a physical surface underneath the ice?
With more stopping power.
With more stopping power. So what happens is there are some cases where, because the dust grains are just on average 0.1 microns in diameter, you're not going to lose a lot of energy if you have, say, 100 keV proton. It can travel through the dust grain, come out the other side, and sort of bombard the other side of the ice. So there will be cases where the cosmic ray will bite the dust. And in those cases, you can actually completely obliterate your grain and just blast everything off into the gas phase, which is an interesting thing, which I am going to be looking at in the future at some point. But yeah, generally speaking, the cosmic rays will just zip right through the dust grain.
Okay, anybody else have questions? All right, in that case, let's thank Chris again.